Pop quiz. During addition of hydrogen bromide to propene, which carbon does the hydrogen attach to? A. The terminal carbon. B. The middle carbon. C. Either one equally. D. It depends on the solvent. Locking your choice. We will reveal the answer soon. In this video, you will learn why more substituted carbocations are more stable, how that drives Markovnikov's rule in electrophilic addition, and how to predict products, avoid traps like rearrangement, and quickly check your work. First, let's start with the basics. A carbocation is a carbon with a formal positive charge. It is sp2 hybridized and trigonoplanar, with bond angles of about 120 degrees. That leaves a vacant p orbital sticking up and down, ready to accept electron density. In electrophilic addition to an alkene, the pi bond acts as a nucleophile and grabs a proton to make a new carbon-hydrogen bond. This step creates a carbocation on one of the adjacent carbons. Which carbon atom gets the positive charge depends on which carbocation is more stable. Finally, the halide attacks the carbocation to complete the addition. More highly substituted carbocations are generally more stable because they experience greater hyperconjugation, where neighboring CH bonds help delocalize the positive charge. Electrons in nearby carbon-hydrogen sigma bonds can gently overlap with the empty p orbital and share a little electron density, which stabilizes the positive center. The more neighboring carbon-hydrogen bonds available for hyperconjugation, the greater the stability. There is also an inductive effect. Alkyl groups have electron density that is more polarizable than hydrogen. Through the sigma bond framework, they push a bit of electron density toward the carbocation center and help stabilize it. Put it all together and you get the trend. Methyl carbocations are the least stable, followed by primary, then secondary, while tertiary carbocations are the most stable. On top of that, allylic and benzylic carbocations gain even greater stability because they can delocalize the positive charge through resonance, a factor that's often even more stabilizing than additional alkyl substitution. Time to reveal the answer to the pop quiz. When hydrogen adds to the terminal carbon, it creates a more stable secondary carbocation on the middle carbon. Then bromide attacks that site, giving isopropyl bromide. This is Markovnikov's rule in action. The pathway that forms the more stable carbocation proceeds faster and wins. So far, we have defined carbocations, explained hyperconjugation and the inductive effect, and ranked stabilities. Want to lock this in? Your personalized practice test and flashcard set are all waiting for you. Tap the link and give yourself a quick check. Now, let's apply this to a real case with a twist. When hydrogen chloride adds to 3-methyl-1-butene, the protonation can leave a secondary carbocation. To stabilize it more, a nearby carbon can slide a hydrogen along with its bonding electrons to shift the positive charge to a tertiary position. That hydride shift makes a much more stable tertiary carbocation, which is then attacked by a chloride ion. Resonance can change the story. In an allylic carbocation, the positive charge sits next to a double bond, allowing it to spread across two carbons through resonance. This resonance stabilization can outweigh the effects of simple substitution, sometimes leading to mixtures of products that reflect the different resonance forms. Here are a few quick fixes to keep in mind. First, hydrogen is not aiming for the bigger carbon. It follows the path that yields the more stable carbocation. Second, vinyl and aryl carbocations are highly unstable and not formed in these simple additions. Third, before you commit to a structure, pause to ask if a shift could make a more stable carbocation. Now, here are the guided steps for any hydrohalogenation. First, circle the 2 possible carbocations from protonation. Second, score each carbocation by substitution and by resonance. Third, if a reasonable 1-2 shift can create a much more stable carbocation, include it. Finally, place the halide on the carbocation, and you are done. Let's wrap it up. Carbocations get more stable as the number of adjacent alkyl groups increases, thanks to hyperconjugation and the inductive effect. To predict products, protonate in a way that makes the more stable carbocation. In addition, consider any resonance and watch for possible rearrangements. Finally, let the halide capture the carbocation. Now that you've watched the video, Let's see how much you remember. Head to the link in the description, where you'll find Quizlet content made just for you.